When you examine a water sample from the Black Sea coastal zone at a microscopic level, you find sand, organic matter, and jagged plastic fragments. These are microplastics, particles smaller than 5 millimeters, and they are now a permanent feature of this ecosystem. Monitoring the health of these waters requires analyzing the physical morphology of every particle found. A fragment's shape and surface area dictate how it is ingested by marine life and how toxins are transferred through the trophic chain. However, this creates a massive operational bottleneck. Traditional manual quantification requires expensive laboratory equipment and hours of technician time, making it impossible to scale monitoring across an entire sea basin. Effective monitoring requires an automated system capable of counting debris and structurally classifying millions of highly irregular fragments in real time. Tracking this impact at scale shifts the burden from manual biology to automated data engineering, requiring the implementation of multi-layered deep learning architectures. The natural environment is vast and chaotic, yet analyzing it computationally requires forcing that chaos into the rigid structural requirements of a computer algorithm. This hierarchy isolates our computational tools. Artificial intelligence operates under defined parameters. Machine learning extracts statistical patterns from massive datasets. Deep learning, the innermost layer, utilizes multi-layered neural networks to abstract visual data, essential for identifying microscopic particles. These models cannot parse environmental chaos directly. They require massive amounts of accurately annotated input data to function correctly. The algorithm's accuracy is strictly bounded by the structural quality of this human-provided data. Data abstraction translates physical microscopic debris into the mathematical formats a neural network can process, effectively turning a picture into a grid of numerical pixel values. This dataset is divided into two strict pipelines: the training subset and the test subset. The training subset allows the model to iteratively adjust its internal weights. However, this process carries the risk of overfitting, where a model memorizes specific artifacts instead of learning geometric rules. To prevent this, the test subset serves as a quarantined blind reference. During the generalization phase, the model is forced to interpret completely novel, unseen samples to prove its viability. Engineers analyze failures on the test set, often indicating a lack of variance. Introducing highly varied edge-case data points builds true real-world model robustness. Quantifying microplastics requires a multi-stage architecture that moves sequentially from spatial detection to pixel-level segmentation. The first stage is object detection, utilizing the YOLO architectural family. YOLO rapidly scans an image and draws a spatial coordinate boundary around anything it identifies as a target particle. Our baseline experiment trains a one-class model to detect the binary difference between particle and background. We then progress to a multi-class model, differentiating specific material types. This introduces a geometric challenge. Raw microscopy images have massive pixel resolutions, yet target particles are microscopically small. To process massive resolutions without losing small feature fidelity, the high-resolution image is sliced into overlapping tiles. The YOLO model evaluates each tile individually, preserving spatial resolution to catch microscale features. After analysis, the system computationally stitches the tiles back together. This requires the system to mathematically resolve any duplicate or overlapping bounding boxes created at the stitched seams. A bounding box identifies a particle's location, but lacks the mathematical nuance to define a fragment's true edges. Extracting the actual shape requires pixel-level classification. Microplastics are irregular and jagged, having been uniquely deformed by years of ocean weathering. Mapping this irregularity requires transitioning to semantic segmentation. The system automatically crops the original image using YOLO's bounding boxes to create isolated single-particle microenvironments. We use the UNet architecture to separate foreground from background. Traditionally, training this requires thousands of images where every pixel is hand-traced by a human, creating a significant data bottleneck. We bypass this manual tracing using foundation models, specifically SAM 2.1. It analyzes the YOLO crops and instantly generates high-fidelity pseudomasks that wrap perfectly around the jagged edges of each particle. These precise pseudomasks are fed back into UNet to finalize segmentation training. The resulting masks provide specific morphological metrics, including exact surface area, perimeter complexity, and axis dimensions. Chaining these architectures together provides a level of geometric precision that maps directly back to the particle's origin and potential ecological threat. This multi-stage pipeline is deployed as a functional web application, making sophisticated computer vision accessible to environmental researchers. When a researcher uploads a raw image, the system automatically executes the tiling, spatial detection, and morphological segmentation in sequence. This automation compresses hours of manual laboratory counting into seconds of raw compute time. This advanced technical capability enables high-frequency, continuous ecosystem monitoring across the entire Lower Danube and Black Sea basins. Protecting these water systems depends on our ability to process environmental data at the speed of the current. By automating the analysis of microplastics, we convert a laboratory bottleneck into a scalable stream of ecological insight.